Dear students, welcome to the second lecture of electricity and magnetism. I am Dr. Ul-Haq. So last time we discussed about electrostatics and the related concepts. We somehow briefly discussed Coulomb's law, so we will carry on from that. So now we will elaborate or go into more detail. Last time we discussed, okay, we have Coulomb's law and Coulomb's law due to point charges. And I told you what is point charge is. So I told you the point charge is something that has very small dimensions. So the electric charge is so small that if you have now two charges, one charge here and one charge here, and there is a distance between these two, some distance, say some distance r, and if we consider these charges as circles or spheres, so the radius of the sphere is too small. So if we now call radius of sphere as r, so this r is much smaller than the distance r, very very small, what to say, and then this we call this, then in that case we call these charges are point charges. This is the definition of a point charge, formal definition. And today we will go into more details when we don't have just like one or 2 point charges, but instead we have a distributed charge. So we have multiple charges that are lumped together, and we will calculate the forces and fields due to this distribution of charge. So we have distributed charge means an accumulation of charge but no point charges. We already know, so this is from the last lecture, that for point charges we know that we have Coulomb's law, this statement in the middle, that there is a force that acts on two charges, that is that force is directly proportional to the product of magnitude of those charges. So we have now Q and Q naught, two charges, and this force is directly proportional to Q and Q naught, and this is inversely proportional to their distance. This is the distance between these two, and what we see that it is a vector force, so we have to give it a unit vector r. And there is a related concept that we now call as field, electric field. So instead of discussing forces directly, we go into the terminology of the field. So a field is in layman terms, in ordinary person's terms, a field is something in which another small point charge, I write a definition. So a field, an electric field, is a region field is a region in space where or in which other charges feel its force. So if we have a charge here, there will be a certain space around this charge, like a circular space, where this charge will exert force. and inside this area, or inside this region, there would be some force that would be proportional to 1 over r squared, and as soon as the charges go beyond this area, there will be no force. So this area, this we call the field, and then if we move far away from that area, then we call that we are out of the field of that charge now. So this is the area outside the field of charge. Okay, and mathematically, outside the field of the charge. So mathematically, what we do, we define field as electrical field equals force, that Coulomb force, divided by the magnitude of the test charge. Test charge means the smaller charge. Q naught is a test charge, because the original charge, this force is due to a bigger charge Q. So if you see in this figure, so this is the charge Q that is producing the field, and this is the Q naught that is feeling that field. So we have to divide the force produced by this charge with the magnitude of this charge. So if you write it in a proper way, so you have force on the charge equal to Fe equals Ke times Q naught divided by r squared into r vector. That is the Coulomb force, vector force. And if you now want to calculate field due to this force, that would be equal to Fe divided by Q naught. And you can just simply divide this equation by Q naught, and you are left with Keq over r squared. So you see that the magnitude of this Q naught charge is gone from this calculation. So now we are in a position to calculate electric field from the same considerations that we used to calculate electrical forces. So we have two charges. We have Q1 that has a magnitude 7 microcoulombs, and this charge has a magnitude minus 5 microcoulombs as mentioned, and they have a distance of 0.3 meters, and we are asked that you need to find a field at this location, point P. So because this is a vector problem, so we have to draw vectors and do the stuff according to that. So I just give you a rough estimate. So if you now draw a vector from this charge, so we have to use superposition principle and field principle both to get to this problem. So this is a charge, so this charge will exert a force in this direction like this, and for this charge the field will not be in a straight line but at some angle from this. So and okay, so the positive charge will have a direction pointing toward point P, and we have to keep in mind that this is a negative charge, so we have to take into consideration that the direction of this force will be like this. Positive force, we point out that it is in this direction, then the negative force will have the arrow pointing in this direction. And if we are clear about that, then we can solve this problem fairly easily. So what we do, we just draw these forces according to the situation. So we call this angle as theta, that this the force from charge Q2 makes with x-axis. You see here is theta, and we have an angle again an angle theta here. This formula that we have if a line crosses two parallel lines, then the opposite angles are equal. So that is why this is theta, and we have to define another angle that is to calculate the net field, because it's a vector field, so that vector field will be given by this vector, this orange vector in this shape. And how we reach that? We actually reach that with the help of head to tail rule. So if you have now one vector pointing in this direction and the other vector that is pointing in say in this direction, so your net vector will be this one. I show you this green one. So you have to use head to tail rule, and you connect the tail of first vector to the head of the last vector, and this you get the final vector. But how you determine theta and stuff, other stuff, that is you have to determine. It's simple, I say, but what you need to do that you have to determine the distances. So assume that we are given this distance. This distance is we are already given. This distance is 0.4 meters. So then it would be easy for us to determine this length by Pythagoras theorem. So you use r square equals x square plus y square, square root, whole square root, and then you will get this. So this is now given by 0.5 meters. That is also easy for you. And if now you know a little bit of trigonometry, then you know that in a right triangle, how to determine this angle theta, this one, this angle theta in this right triangle. So that is again tan of theta equals y over x. And this is also easy for you, and from here you will get theta equals tan inverse of y over x. So y you have 0.4 and x you have 0.3, and that is also easy for you to determine angle. And if now you can determine angles, the rest of the diagram is, I think, it's not a problem for you. Why I am saying that? Well, so that I do it for you here so that you are not frustrated how to calculate that. So keep into the mind that we have this situation, and we now have distances. This distance 0.5, this distance 0.4, and now we want to calculate field here, the vector field. So let's calculate field due to Q1 at this point. So for that we use definition of field. So we call this field as E1. E1 we call this. I should use a bit smaller font. So E1 due to Q1 is KE times Q1. We call this Q1, and divided by R square. So you know that QE, that is Coulomb's constant, that is 9 into 10 raised to the power 9 Newton meter square per Coulomb square. I will not write the dimensions, so you should know that the dimensions of electric field are always Newton per Coulomb, that you can determine. So and for charge we have charge Q1 equal to 7 microcoulombs if you read the statement of the question. So that would be 7 into 10 raised to the power minus 6 coulombs. You just change the micro to coulombs, and then we have a distance of 0.4, that is squared. And if you see now, so that would be 63 into 10 raised to the power 3 divided by 0.16. And if you using a calculator, you will get this as 3.93 into 10 raised to the power 5 newtons per coulombs. And you should see from this figure that your field due to charge Q1, it has only one component. So this Q1 and this point P are in line, and if we call this direction as our y direction, this is our y direction, then it has only y component, and for y direction we use j unit vector. You remember that for any vector we have x with I unit vector, y with j unit vector, and z with k unit vector. That is always the terminology that we use for unit vector. So the field due to charge Q1 has only one component, that is the j component, and that component we just from the value of the field that we have calculated. So we call this E1 equals 0 times unit vector I, because it does not have any x component, plus 3.93 into 10 raised to the power 5 Newton per Coulomb with the j unit vector, this field direction. This is our field at point P, field at point P, Q2, Q1. Understood? I hope it's easy for you. Now we determine the field due to charge Q2. Field Q2 charge Q2. So it's again it would be two components. So that would be E2 vector would be E2 field times x unit vector plus E2 times j unit vector. So this is the magnitude, and these are the unit vectors along with it. And we first determine the magnitude E2. So magnitude, we use the field formula. So E2 simply its magnitude. Okay, I put mods so that you are not confused. So E2 in mod shape, that is Ke times Q2 divided by R squared. And now this time, which R distance we will use? This distance that we have here, because this is the distance from charge Q2 to the point P. So that's also easy to remember what we are doing. And Ke is again 9 into 10 raised to the power 9, and Q2 is, I think we have 5 microcoulombs. So 5 into 10 raised to the power minus 6 in shape of just coulombs, and the distance is 0.5, so we just square that distance. And at the end of the day, what we get, I'm using calculator in parallel, so that is 45 divided by 0.25, that is 1.8 into 10 raised to the power 5 Newton per Coulomb. So this is the magnitude of the field due to charge Q2. But as you see from the figure, this is not a straightforward thing here, because now the charge is not, the field is not pointing in any particular direction. So here you see that the field has the E2 field is in this direction. So this is not along x or y axis. So we cannot assign only one component to it. So for that we need to determine this angle theta, so that we have to be sure that E2 has two components. So one is I write it explicitly because the field is not pointing in along any axis. So now we have E2 vector, that is E2 x unit vector plus E2 y unit vector, E2 x and E2 y. So I write in specifically in this shape. So E2 x is okay. So I made a mistake, a little bit of mistake here in writing when I was writing components. So here you also use E2x and E2y here, and then E is the sum vector sum in terms of magnitude of this. So we have determined E2, and now we want to determine E2x. So E2x, the x component of the field vector in terms of E2 is E2 times cosine of theta, and E2y is E2 sine of theta. That is also easy to remember. These are the components, and we know now we have this information of E2 that we calculated. This is 1.8 into 10 raised to the power 5, but we don't know theta yet. And for theta it's easy. Again, I told you before, that is the relationship is tan of theta is equal to y over x, and y is 0.4 and x is 0.3 in terms of distances, and from here you can get that is inverse tan of 0.4 over 0.3, and from here you will get an angle of 53.1 degrees. It's a simple calculation if you use the calculator. So we have now theta, that is 53.1 degrees, and you just have to plug values of theta here. So E2x will be E2 magnitude that we calculated and cos of 53.1, and similarly E2y is E2 sine of 53.1. So I use calculator in parallel. So we have now sine of cos of 53.1. This is 0.6. So here we would choose 1.8 into 10 raised to the power 5 multiplied by 0.60, and for E2 sine of theta or E2y we use 1.8 into 10 raised to the power 5 times sine of 53.1, that is 0.799, and at the end of the day you will get E2x component equal to E2y component equal to 1.43 into 10 raised to the power 5 Newton per Coulomb, and for the x component we just compute this thing, that is 1.8 into 0.6, and that is 1.08 into 10 raised to the power 5 Newton per Coulomb. And now if you want to write this in vector form, vectorial form, that is also easy. So we have now E2 in vector shape, that is E2x I unit vector plus E2y j unit vector, and E2x we have now 1.08 into 10 raised to the power 5. And remember, although in the formula we have to write like this, but if you see from figure that E2x component, so pay attention please. So if you see now here, so you see that E2 is pointing in this direction, so E2y will be pointing down, and if we have taken for E1, we have taken the direction E1 as positive, so we have written E1 as 3.93 with a positive sign. So now this vector is opposite to that, so we have to write, if this is a positive vector, then this would be a negative vector. And for E1 we have taken this one, for E2 we have to take this one because E2 is pointing downwards, so its y component will also be pointing downwards along the y-axis. So we have to write minus sign here. So we write, when we are writing it formally, as (1.08 into 10 to the power 5 Newton per Coulomb in I unit in I direction, and minus 1.43 into 10 raised to the power 5 Newton per Coulomb in J direction, because it is the positive J is in upward and this is in the downward direction, so we have to write minus with it. And this is the net field, okay, the components of the field. So the field at point P due to Q1 and Q2 is due to Q1 it is E1 that we have written before, that is 3.93, so 0 times I unit vector plus 3.93 into 10 raised to the power 5 Newton per Coulomb in the J direction, and due to E2 we have written just now 1.08 into 10 raised to the power 5 Newton per Coulomb in I direction, minus 1.43 into 10 raised to the power 5 Newton per Coulomb. So this is the method that you will use whenever you are dealing with vectors and scalars. Although it looked somehow simple problem from the figure, but what you have seen here, that it takes fair bit of time and effort to calculate the components and determine the directions and determine the angles. And for your assignment you can calculate the net field E, that is the summation of these two fields, the vector sum. So you just add x component to x component and y component to y component, then you will get net E, and that I leave on you as an assignment. I think one problem and a small definition of electric field is enough for today's lecture. We will resume from here and we will discover electric field due to distribution of charges. So today we could not go to distribution of charges because of the length of the lecture. So we only determined field due to point charges, 2 point charges simultaneously, one Q1, the other one is Q2 in vector form. And next time we will go on to explore dipoles and fields due to dipoles and distribution of charges. So till then, bye bye.